So whenever you want to prove that a function is big O of another, you have to go back to your definition, and this is just honestly something you should remember or memorize. So a function is big O of another if it matches this equality, and we have to pick C and K values, so these are constant values, where this inequality holds true. And this is just saying like f of x grows slower or the same rate of g of x. And so I've also included this like massive inequality, and this is just something good to remember. It's good to remember the general growth of functions and how they relate to each other for like the most simple ones. So this is something you should memorize, and this is helpful because like earlier things are always big O of things that are greater than it. So like log n is going to be big O of root n, or you can say, log n is big O of 3 to the n. As long as it grows at a slower rate, then we can say it's O of that function. So I have some problems. We want to show whether they are true or not, and we want to use mathematical reasoning. And just this means like I want to prove with actual values of C and K. And so for these problems, there's not always going to be like one specific correct answer. A lot of the times the graders will accept multiple C and K values as long as you're making your inequality true. So let's get into it. So let's rewrite as our definition. So we're just rewriting this as an inequality. And remember, we want to have some C value where this is true. And this is true for x greater than some K value. So how do we determine what C value we want to use? So the nice thing with using inequalities is I can manipulate my original statement. So I know that 2n plus 1 is less than 2n plus n. That's a fact, right? Because we know 1 grows slower than n. So yeah, this goes back to why remembering this is helpful. And I also know this is actually equal to 3n. We're going to add those together. And so we want to show for some C value, this is greater than this chunk. And this makes it a lot easier. We know if our C value is 3, then it will be greater than or equal to our original function. So we have proven true if C equals 3, and now we need to show, I should say n. In this case, we're using n, not x. And K equals, well, think about it. So if we have 3n is less than or equal to 3 times n, 3n, we know for sure that this is going to work for a bunch of different K values. And that's where like they'll technically accept multiple answers. So I could say like K equals 2, K equals 3. In this case, I'll just say K equals 1. So yeah, we've proven it to be true. Okay, so let's try to prove this. So again, let's rewrite this as an inequality. And this just is from our definition. Now remember, you can manipulate inequalities, so I can divide both sides by n, right? And actually I can just, well, no, let's not do that. Okay, let's divide both sides by n. And now this makes it a lot more obvious. So this is not true. And the reason that is because there is no constant value that will always be greater than this, right? Because say I make this like 5, well, as like x goes to infinity, well, this is always going to be greater than whatever constant you choose here, if that makes sense. So it doesn't matter what c or k value you have, this is always going to be false. And for these, you can just say like, oh, this is false because there are no c or k values. Oh my gosh. To make this true. Wow, pretend like this was good handwriting. I don't know what's wrong with my stylus, but anyways, moving on. Okay, so we want to prove this as well. This is a little bit more tricky, but yeah, we still got this. Okay, writing this as an inequality. We have our c and then times just the given. Okay, so again, let's try to rewrite this to make it easier. So the way that I thought of this problem is, well, first, remember you can divide n on both sides, so this still holds true. This is equivalent to the above. And now, let's try to get this in a similar form to this. And this is just because like it's visually hard to like pick c and k values that make this true. So remember, this will be the same thing as here. That's equivalent because like if you have n to the 1/2, then remember you can like move your exponent out here and that would cancel. And then c times root n. So going back to our inequality thing here, we know that log of something is going to be slower, or like big O of root of something. Oh, no, sorry. We're looking at these two. We know that log grows slower than just linear growth. Because we can think about like, oh, this is x and this is some other function x. So we know that we can say if c equals 2, then we know that this is always going to grow slower than that. And again, you can kind of just pick any k. This holds true. So yeah, this statement is true. And actually, I want to go to Desmos and show this. So remember, our original function is this. I just plug that into Desmos. So if you actually look at it, root x root x starts off growing faster, which is good, but then we have a period where x log x is growing faster, but then it gets bypassed by x root x later on, and then it will continue, and it will always grow bigger. So we've proven that to be true, but we had to pick a c and k value where it's always going to be greater. So what we did was we said, oh, if we multiply this by 2, it's always going to be greater. And if you look at it, yeah, it is. And so I could have chosen k to be 0, but I chose k to be 1. So that's really going to like, that goes to show like why you need to pick c and k values. And yeah, let's go back. We have one more problem. Okay, again, write this as an inequality. C times n log n. Okay, this is going to take a little more imagination, and you have to go back to your log rules. Remember that this is equivalent to doing like n times n minus 1 times n minus 2, dot, dot, dot. And with your log rules, you can rewrite that as, oh my gosh, okay, n minus 1, dot, 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 until times log of 1. So this is just equivalent to above. I'm just rewriting this in a form that makes more sense. Now I know that this is actually going to be less than, let me just copy this. Remember, if I can write something that's greater than it, but still less than or equal to this, then we can include it. So I know that I can read, this is always going to be greater than this. And that is less than c to n log n. Now, this is just this repeating n times, right? So we can rewrite this inequality as n log n, right? Okay, so now that we've shown that, like this is always going to be less than this, and this is true if c, well, c can just be 1, and k, I just normally choose 1 as well, k equals 1. So yeah, we've proven this is true.